Now we will see some kind of specialized kind of neural networks. This one is called neural ordinary differential equations. So we can think of a multi-layer perceptron in which we have multiple hidden layers, and each one of the hidden layers has a state, so an activation state. So they produce an output that we will call h of t. This would be, we can consider it to be h of t plus 1, h of t plus 2. So each one of these layers can be understood as a transformation of an internal state at discrete times. But these discrete times, we can think of the h of t as the solution of a differential equation, so that how the h of t evolves over time depends on some function that depends on itself and time, and we can impose some kind of a special shape to this change, time change. So for instance, here we can say, okay, this is a matrix with some weights that depends on the weights and time, and then they are applied to the internal state plus some bias. So it is a very simple function, and then each one of these layers can be understood as sampling this the solution of this differential equation at these given times. And then if we want to solve the equation numerically, what we would do, for instance, if we apply Euler's method, would be the next state will be the current state plus f. And this is somehow the same kind of equation that we have graphically in these kind of ResNets. So ResNet, you have an internal state, and then what you have here is the addition of the internal state plus some function that acts on this internal state. So this is the same as we would be doing here, and then the same for the next layer, the same for the next layer, and so on. There is a restriction here that all the internal states have to be of the same dimensionality, but otherwise they would be kind of similar, conceptually similar to what we said here. And liquid neural networks, they have a fancy name, and it is nothing more than a specific family for this ordinary differential equations formulation, in which we have this f that depends on h and t, and then there is some parameter 1 over tau, and this f affects the h, and they affect the bias. So they have been used to model brain networks, so neural networks coming from the brain, and then somehow they have these terms f, they have an interpretation in terms of excitation, inhibition, and so on. So it is a special case of these neural ordinary differential equations in which the update of the state is done in this way.